Today we're going to take a look at section 2.5. In 2.5 we're going to be talking about inverse functions. So inverse is the idea of undoing things. So every time that we work with order of operations, we work from the inside out, right? So as we do the inverse of that, everything is going to go backwards and we're going to be working from the outside in. Before we can even worry about doing inverse functions, we have to work with functions that are a specific type that are called one-to-one. So let's start with that. A one-to-one function is a function for which every element in the range corresponds to exactly one element of the domain. Now you've seen a definition like this, at least similar to this before. It was the definition for a function. But it was a little bit different. It didn't say every element in the range corresponds to one element of the domain. It had the words backwards. It said every element in the domain corresponds to exactly one element in the range. So in order for it to be a one-to-one function, it actually has to satisfy the function definition that we already had, plus this extra condition about being one-to-one, okay? So in particular, what we want to make sure, if we're thinking about it, we can do a couple of things. One thing that we could do, which we did before, is to put sort of these categories where I put my domain values on the left. So that would be my 2 and my -2, and my range values on the right, and there's only a 4. And what we want to make sure is we want to make sure that when we draw these arrows, that one element on the left corresponds to exactly one element on the right, and one element on the right corresponds to exactly one element on the left. So when I did functions, this was fine. I can do this, which is how this is lining up. This is a function. There's no problem with that. But if it's a one-to-one function, it can't do this. It cannot have two items coming from the domain mapping to one item in the range. So this one is not one-to-one, because the element 4 in the range has two items that correspond to it. If we do the same sort of thing with the next set, we have 3, 5, and 7. And then I have 2, -2, and 8. So 3 corresponds to 2, 5 corresponds to -2, and 7 corresponds to 8. This is considered one-to-one. Okay, so one-to-one mappings like this are what we in the Christian faith would consider what marriage is, right? You have one man, one woman. That's what we consider, okay? So that's the idea, if you want to think of a contextual idea for how this works back and forth. That's not what happened when I did. Do you remember the example I did for functions? I did, let's see if I can remember which one I did in here. I think that I did children in my domain, and then I did their biological mother in the range, right? So I can have multiple children going to the same biological mother, and that's a function. But it's not a one-to-one function because we don't have just one child for every one biological mother. So that one would not be considered one-to-one. We had a line test when we did our functions. It was called a vertical line test. And we said if I drop these vertical lines through a graph and it only crosses once, good to go. It's a function. We have the same thing for one-to-one functions. It's just called the horizontal line test. So instead of dropping vertical lines, I'm going to be drawing horizontal lines. So if you can imagine, do I have an example on this? On the next slide I do, yeah. This one right here. So we've seen how to draw these. You've been working on that in a couple of sections in chapter 2 so far. This is the graph of the absolute value of x. What does the graph of the absolute value of x look like? It's a V. How do the 2 and the 1 that are in this sort of setup change things? Let's start with the 2. What does the 2 do? Okay, it is a -2 and it moves it to the right 2. And what does the -1 do? It moves it down 1. So in terms of my graph, I have, like you said, the basic V-shaped graph. But instead of my origin being the vertex, or the corner of it, let's use this right here, I'm shifting it right 2, and I'm shifting it down 1. So this is the opening spot. And then I go up 1 and right 1. Up 1 and left 1, and then I'll connect them. So my graph ends up looking like this. So this is the graph that we're referring to. So the horizontal line test says that if it is a one-to-one function, this is a function, right, because it passes the vertical line test. If I were to draw vertical lines, let me change the color, we'll do blue. If if I were to draw vertical lines down through all these, it would always cross once, right? So it's definitely a function. But what happens if I try drawing horizontal lines? Yeah, there's some locations, in fact most, right? Most of them that I've drawn anyway, where they cross twice. And when that happens, this is not one-to-one. It's a function, but it's not one-to-one. All right. The reason we need one-to-one functions is because we're about to switch things around. Okay, we're about to do the inverse operations that I mentioned at the very beginning of the lesson. And in order to be able to do inverse operations, I have to have functions that are one-to-one. And here's why. Visually speaking, what I'm going to be doing, I'm going to be flipping things along an axis. Now, we've talked about symmetry where we flip things over the x-axis and over the y-axis, right? Well, what we're going to be doing on these, I'll just use on this graph right here since it's still drawn in, is we're going to be drawing them along the line y equal x. That wasn't very good. Let's try again. That's a little bit better. So we're going to be flipping them along this line right here. And if I don't have a one-to-one function and I try to flip it along that line, the result will end up with something that's not a function at all. That's actually what happens. So in order to ensure that my answer is a function, I have to start with a one-to-one function to begin with. And I'll draw pictures of these where they make sense on the graph as we do a couple more later. So an inverse is what we're going to be looking for. Has a specific notation. It has a little -1 exponent, f to the -1. It does not mean reciprocal. It does not mean multiply by -1. It does not mean raise something to the power -1. It's a notation. Just like f with the parentheses x does not mean we multiply f and x together, right? It's a notation that says I have a function, the variable is x. This notation, f inverse of x, is simply the notation that indicates it is an inverse function. It undoes the original function. There's really just two steps to finding an inverse. The first thing is you switch the x and the y variables. So x becomes y becomes x. And then the second thing is you solve for the new y. The solving for the new y can take on a variety of forms. It depends on what kind of equation you were working with to begin with, right? So that's what we're going to actually spend the majority of the time doing on these today. So in order to actually make sure that these work, we want to at least conceptually check. We don't have to actually physically check unless you need to, that they're really one-to-one. Because if they're not one-to-one, they're not going to work. Okay? So the first graph is the graph of x over 2. What is that a graph of? You know? Okay, so you could put in a calculator, or you could remember that this is the same as 1/2 x. What is it? It's a line. Thank you, David. It's a line. So it's a line. It's not a horizontal line, right? It has slope. It has a slope of 1/2. So it's definitely one-to-one, right? No problems. I can cross horizontal lines through any other line just fine. No problem. It's going to cross one time. So this is one-to-one. So what I'm going to do then with it is that I'm going to, like the directions over on the previous slide says, is I'm going to switch the x's and y's. The left-hand side, f of x, means y. So now I'm going to write it as x, and the x becomes y. So this is sort of step one. I'll just label them as we go so that if you're looking back, you can remember what we were doing. Step one is just switching them. Step two is to solve for the new y variable. What would I need to do to solve this for y? Yep, I need to multiply by 2. So I have 2x on the left, and the 2's cancel on the right, leaving me with y on the right. This is the inverse function, okay? And if I were to write it in the inverse function notation, the y would be replaced with the little f inverse that we talked about on the previous slide, and it would look like this. If you forget that very last step, it's okay. It's still an inverse function. It just doesn't show it in terms of its notation. Okay, so the most correct answer is to actually have that notation on there at the end. Now, I'd like to graph both of these, at least in a sketch kind of format, so you can see what I was talking to you about the reflection. So if I were to graph 1/2 x, and these aren't going to be perfect graphs, but they're going to be a good idea. Let me get a scale on here. The graph of 1/2 x and the graph of 2x both cross the origin both cross the y-axis at the origin right here. So one of them has a slope of 1/2, which means I go either up 1 and over 2, or you can think of it in terms of the numbers 1/2. I'll do this one because it's easier to plot. So the graph looks something like this. Now let me get my slope right, and then I'll shift it if I need to. No, that's not too bad, actually. Okay, so there's that one. The other one has a slope of 2, which means I go up 2 and right 1, down 2 and right 1. And that graph looks something like this. Let me shift it. Okay. And I didn't draw it in yet, but let me draw in the graph of y equal x. That one looks like this right here, dotted line through the middle. Can you see the reflection taking place? Can you see how this piece right here gets reflected up here? And how this piece down here gets reflected up here, or vice versa? There's a reflection over that line y equal x as we are working with inverses, and that will always happen. So it's not a bad check step if you do have a graphing calculator to graph both of them. Make sure your axis looks like a square axis. Sometimes your axis in your calculator, the default is the -10 to 10 and -10 to 10. But if you take a look, this is not a square shape, it's a rectangular shape. So you need to be a little bit careful as you're looking that you don't get thrown off by the fact that you don't have a square window. Right, it's a rectangular window. There's a zoom function called zoom square, if that helps you. But this is the correct answer. This is our inverse. Let's look at the next one. It's a little more complicated because it isn't a line, right? That's the graph of a cube root. It's a cube root graph shifted how? Right 9, okay? But it's a cube root graph, correct? So if I were to try to draw this graph, just thinking about whether or not it's 1-to-1, it has this basic shape, right? More or less, that's what we drew. It's shifted, that's why I don't have my axes on there. But can I draw my horizontal lines and be good to go? I can. It's perfectly fine to do so. So this one actually does have an inverse. So my step 1 is going to be to switch x and y. So I have x on the left now, and I have the cube root of y minus 9 on the right. That's the easy step. Then we have to solve it, and it's not quite as clean and straightforward as the last one. So I am undoing everything. So order of operations moves from the inside out. When I'm finding inverses, I move from the outside in. So what is the most outside operation that's happening to the y on the right-hand side? The cube root. So the first thing I have to undo is the outermost operation, which is a cube root. And how will I undo a cube root? What's the opposite? Say it again. You cube something, yeah. So we're going to cube both sides. So now I have x cubed on the left, and then the whole point was that this would cancel, right? So my cube root and my cube cancel on the right. So I'm left with the y minus the 9. That's it. Again, I want to solve for y, so what's the next thing I need to do? I need to add a 9. So I have x cubed plus 9, or you could write 9 plus x cubed, that would be fine, equals y. That's my inverse function. The notation for it looks like this. F inverse of x equals, and it's x cubed plus 9. So it looks something like that. We'll see if we can get the document camera to work, and I'll show you what the screen looks like, because I don't want to necessarily draw this always by hand. I'd like for you to see that it works in your calculator too. He's like, are you kidding? I think it'll show it right at it, though. All right, so what I'm going to graph is I'm going to graph the first equation that I was given. I know it's not showing up on my screen anymore, but the f of x equals cube root of x minus 9. And I'm going to graph the one that we found, which was that y equals x cubed plus 9. So on the all right, I think that's okay. We have the cube root. If you don't know where the cube root is, it's actually underneath the math button, so you can hit second math. I'm sorry, just hit math. and there's a cube root is number 4. So it's number 4. There's cube root of x minus 9. And then there is the one that we got, which was x cubed, x to the power 3 plus 9. And I'm actually going to have it draw that line y equal x in there so we can see the pivotal reflection line and make it a little bit easier. So I'm going to do the zoom, and there's one that says zoom square. It will be easier for us to see the reflection if it's in a square window, so I'm going to choose number 5. Okay, so that's that first one, that cube root we were expecting. Can you see the symmetry? Can you see the fold along the line? So at least visually speaking, our graph makes sense. It's a good visual check step. All right. We may come back to this, we'll see. All right, our third one is definitely the most challenging for solving for y. This graph is a rational function. It would be a good idea to check it to make sure that it actually is 1-to-1. I'm going to tell you that it is, just to save us a little bit of the time in doing so. You do have a 1-to-1 function. But I want to actually do those steps that we did before and show you how they can play out when things are even less structured. So I have the y replacing, or the x replacing the y, and then the y's over here replacing the x's. And do you see why this one's going to be more difficult to solve for y? Why? There's a y in 2 places, right? And there's no way to reduce the numerator and the denominator of this, in spite of the fact that many of you keep trying to cancel things for me. You can't. It doesn't work. So what we're going to do is we're going to have to get rid of the fact that there's a denominator first. So the first thing we're going to do is we're going to multiply both sides by the y minus 5. So on the left, I will distribute this. Okay, the x will distribute. So now I have xy minus 5x equals. And then on the right side, these two cancel. So I'm left with y plus 3. Okay, is everybody good so far? All right. What we need to do is we need to collect all of our y's now on the same side. So I'm going to shift. It doesn't matter which way you shift it. Let's shift this y over here to the left. So now I have xy minus y, which they cannot be combined. We'll have something else we can do in a minute. Minus my 5x. These cancel, and it leaves me with 3. There's still that 5x on the right hand or on the left hand side, so I want to move it to the right hand side. So I have xy minus y equals 3 plus 5x, or you can do 5x plus 3. Once you've isolated all the y's on the same side, you can notice that both of those pieces have y in them, which means we can factor them. Yeah, so I can take a y out. So when I take the y out, I'm left with x minus 1. And on the right-hand side, this equals 3 plus 5x. The goal is to leave y alone, and so right now the y is being multiplied by x minus 5, or x minus 1. So what do I need to do with the x minus 1? Yeah, I need to divide it. So I end up with, of course, these canceling, which was what I was shooting for by the division. I have 3 plus 5x on top, and I have x minus 1 on bottom. And the inverse notation would leave me with 3 plus, or with f inverse of x as 3 plus 5x over x minus 1. So it's very common when you start with a rational function and you do its inverse that you end with a rational function as well. That's sort of an expectation. I will tell you, if you look at the graph of this, both of these together, it's really confusing to see the reflection because there's a lot going on in a rational equations graph, all right? It's not impossible, it's just harder to see than the other ones. Let me show you real quick just so that you're not unexpectedly surprised by it if you try this at home later. So we'll put our two equations in, the one we were given and the one we found. and that line y equal x. So to start with, we have x plus 3 over, why didn't it bounce? There it goes. Over x minus 5. We had 3 plus 5x over x minus 1. And we're going to have our line y equal x, and I'm going to do zoom square, which is number 5. So here's that first graph. It is, in fact, a one-to-one function. And you almost have to think about it in pieces, right? Because you can see this piece here at the top, how it sort of has this flipping nature, right? This little piece right here is flipping over to this top piece right here. And you can see it happening over here as well, but this is a very confusing graph. But it does still have that reflective nature present as we take a look. All right, we have one more of this type. We won't graph this one since we've done a couple of them now. This one is interesting because it has a condition on the end that tells you that x is greater than or equal to 0. So ignore the condition for the moment and tell me what this is a graph of. It's a parabola. And if I have this parabola, it's actually a parabola opening downward because of the negative in front of the x squared. So its basic shape looks something like this. And what would happen if I try the horizontal line test on this? It's going to fail. Right? It's going to fail. And so the reason that we have this condition here, x is greater than 0, is because what it wants us to do is only look at half of the parabola. It's a tricky way to be able to still do the problem, right? By eliminating the part that's causing the problem when I actually do the horizontal line test. So that's why that's showing up there. This x is greater than or equal to 0 is telling you you have half of a parabola. And half of a parabola does, in fact, pass the horizontal line test. So we are able to find this inverse. So we're going to take, and we're going to do step 1, where I write this as x equals 1 minus y squared. What would be my next step as I start to solve? Moving from the outside in. The squared is attached to the y more closely, so we're going to take away the 1 first. Yeah. So we're going to move the 1 first. So I have x minus 1 equals negative y squared. Then what? What's that? Yeah, we got to get the negative to move before we can deal with the square root as well. So we're going to divide or multiply by a negative 1. It just changes all my signs. This is now negative x plus 1. Or if you prefer, you can write it as 1 minus x. And then finally we get to take our square root. So I have y equals the square root. And again, you can write negative x plus 1 or 1 minus x. We do have to be a little bit careful. We put a square root onto something. Typically speaking, when we do that, what do we have to do? We have to put a plus or minus. I say typically because we don't have to here. And the reason that we don't have to here is because we absolutely, beyond a shadow of doubt, know what's happening with my x value. My x value is greater than or equal to 0. So I actually don't end up having to worry about the plus or the minus because of the definition part at the beginning on how I have to restrict my domain. And so therefore it restricts the range as well. So I don't end up needing the plus or the minus as I'm working with these. So my f inverse function ends up just being the square root of negative x plus 1. Any questions on those? So what we've been looking at so far is verifying that, in fact, inverses check out sort of visually speaking. And even as I said it didn't really prove it. It just sort of gave us this, I don't know, sort of feels comfortable. We looked at it and it says it looks reasonable. It's a good check step, right? It didn't verify it for sure, but it seemed reasonable by looking at the graph. Agreed? Yeah. So what we're going to do next is we're going to actually look at how we can verify things, our inverses, algebraically. Okay, so we looked at it from a graphical standpoint. It gave us nice, warm, fuzzy feelings inside, but it didn't really prove it. This really proves whether or not things are inverses. If, in fact, functions are inverses, they can be composed, like we saw happen in section 2.4, so that when we do the composition in either direction, F compose X or G compose F, F compose G or G compose F, we get back X. And you actually test both pieces. We test two things in order to test to see if they are inverses. To be honest, if one of them fails, you don't necessarily have to show the other one fails. If it fails once, it's going to fail the other one too. You don't have to double check your failure. But in order to prove that it works, it has to be proven twice. That's the way it works. So let's take a look and I'll show you what this looks like. So we have two functions here, f of x and g of x. And we're just going to go in order the way that it was presented. We're going to do f compose g of x. So obviously we haven't graded and seen how well you did with composition of functions. I hope you did very well because you're going to need it right here. So we're going to take that g of x function, that's this, and we're going to substitute it into the other function for x. So my f function is 20 minus the 5, and the x gets replaced by the negative 0.2x plus 4. Okay, that's the replacement step. And then we're going to simplify. So as we simplify, we will distribute. So I have the 20 at the beginning. What is negative 5 times negative 0.2x? What's my sign first? It's positive. What's 5 times 0.2? Do you know what 0.2 is as a fraction? It is 1/5. What's 5 times 1/5? 1. It is 1. You can write 1x or you can just write x. On the other one, what would we have if I take negative 5 times the 4 at the end? Negative 20, which is a very good thing because what's going to happen to my 20s? They cancel, they add to 0, and I'm left with simply x. That works. That's what I'm looking for. I'm looking for it to equal x. So then I move on to test the other direction. So this is sort of one direction, and then the other direction is g compose f of x. So now, instead of what I had highlighted before, I'm going to be taking this expression for f of x, and I'm going to be substituting it into x in the other expression. So I have negative 0.2 or 0.2 if you prefer. The x gets replaced by 20 minus 5x. And then I have, I'm sorry, that's not right. Too much zooming in and out. Let's try again. No, it was. I wrote it right. 20 minus 5x. And then my plus 4. There we go. Back on track. Okay, so just like last time, we're going to distribute this through. So I have negative 0.2 times 20. Any ideas? That is negative 4. And then I have negative 0.2 times negative 5, which is still 1. Positive 1x. And I have my positive 4 at the end. And you notice that your 4s add to 0. They cancel out, leaving me with simply x. So these are, in fact, inverses. Are they inverses? The answer is yes. If you simply answer yes and don't show any work, you're probably not going to get any credit because then it just becomes a guess. You guessed that they were, or maybe you looked at a calculator screen, but that's not what they're asking you to do. They want you to check it algebraically. Okay, is that good? Okay, we have 2 more to try with this same idea. So on this one we have f of x is x minus 3 over 5, and g of x is 5x plus 3. Okay? It doesn't really matter which way you start. Honestly, just alphabetically speaking, I always will start with f and then do g. But you can do it in another order, it doesn't matter. So here is my value for g, and it's going to evaluate and be substituted in for the x in the f of x equation. So I have 5x plus 3, and then I'm subtracting my 3 off at the end, and then we're dividing by 5. So while I put the parentheses in there to show where I put my substitution, they're not really necessary for the operations, right? I'm not multiplying anything. I'm not distributing anything like I was in the last problem. they're rather irrelevant. So I could eliminate these parentheses and simply simplify what I have remaining. So in particular, you see the adding the 3 and the subtracting the 3, right? Those add to 0. So that leaves me with 5x over 5. And what happens when I do 5x divided by 5? Yeah, we get x. So this checks out when I do it from that direction. Now we'll do it from the other direction. G compose f of x. So again, did that again. There we go. I need to take all of what f of x is equal to, and I need to substitute it into x in the g equation. So the 5 is there, and then I have the x minus 3 over 5, and then I have plus 3. The parentheses actually are quite necessary on this step. They do have multiplication here, but you'll notice that there's a 5 here and a 5 here, which means multiply by 5, divide by 5, they cancel, right? That leaves me with x minus 3 on top of a 1, so it's just x minus 3, plus the 3 at the end, leaving me with just x. So are they inverses? Yes. You do need to make sure you answer the question, yes or no. I mean, that was the question that was asked. Everything we did already was the work to support it, but I need to know that you know what you found when you're done. And that's what you're giving me when you tell me yes or no. All right, let's try one more. So I have f of x is x over 2, and g of x is 3x. So we'll do f compose g of x. So I'll take this component, and I will evaluate it into our f function, substitute it in. So 3x over 2. You can write 3 over 2 as 1.5 if you wish. But the nuts and bolts of what's happening here is that this does not equal x, right? This one fails. It does not equal x. So are they inverses? And the answer is no. So oftentimes when the answer to something is no, it's easier when it's yes than when it's yes, because you have less work to do. You find that the answer doesn't work more quickly than something does. So the answer is, in fact, no.